Hello dear students, welcome back to the lecture series on abstract measure theory. We were discussing the relationship between improper Riemann integral and the Lebesgue integral. This is the fourth lecture in this section, and today in our lecture we'll try to evaluate the integral with the help of Lebesgue theory. We'll try to evaluate the integral 0 to infinity sin x by x e power minus xt. Okay, so we have following theorem. The statement of the theorem is if t greater or equal to 0, if t greater or equal to 0, then we try to prove this 0 to infinity sin x by x dx is equal to pi by 2 minus arc tan t. Arc tan t means tan inverse of t. Okay, this holds. Proof. We will prove this theorem in two steps, in two cases. First, we assume that this t is positive, and in the second case we assume that t is equal to 0. So let us fix some t naught greater or equal to 0. Let's fix some t naught greater or equal to 0 we try to prove that this integral 0 to infinity sin x by x, okay, this is not sin x, just sin x by x, this is sin x by x into e power minus xt, e power minus xt dx, okay, e power minus x t naught dx is equal to pi by 2 minus arc tan t naught. Let's take the case 1. Case 1, we assume that this t naught is positive. If t naught is a positive number, okay, if t naught is a positive number, for each fixed t positive, for each fixed t positive, we note that we note that e power minus mod of e power minus xt sin x by x, this thing, it's less or equal to e power minus xt. Okay, but this function okay, for t equal to 0, so this will be less or equal to 1, but the function 1 is not integrable, okay, because this is equal to the infinity, integration of 1 dx if t is equal to 0. But for t positive, this the integral of this function exists, and the integral 0 to infinity e power minus xt dx, it is equal to e power minus xt over t 0 to infinity. So let's take the limit infinity, since t is positive, so this will be 0, minus at 0 its value is 1. Okay, so the integral is equal to minus 1 over t, which is the finite thing for each t positive. Okay, so therefore the integral 0 to infinity mod of e power minus xt sin x by x dx exists. So this means that the Lebesgue, the function is Lebesgue integrable. So therefore Therefore, e power minus xt sin x by x is Lebesgue integrable over 0 to infinity. It's Lebesgue integrable. Now let's define this function. Let f of t is equal to 0 to infinity e power minus xt sin x by x dx. So we show that f of t naught is equal to pi by 2 minus arc tan, no, minus arc of tan t naught. And then this f, it satisfies the following properties. So this actually we try to show that this function is dominated by some Lebesgue integrable function. Then we can pause the limit, then we can apply the limit t approach infinity f of t is equal to 0 to infinity limit t approach to infinity e power minus xt sin x by x. So if we take g of x equal to, if we define g of x is equal to 1 if x belongs to the interval 0 to 1, the closed interval, and if I define g of x is equal to, it's a function e power minus x for x greater than 1, then we can see that this f of this function e power minus xt sin x by x, then g is Lebesgue integrable, and this function is obviously Lebesgue integrable. You can easily verify it because you can find its integral mod 0 to infinity, improper integral of the mod. That's the finite thing. So we can say this function g is Lebesgue integrable, then g is Lebesgue integrable, then g is Lebesgue integrable, and the mod e power minus xt sin x by x is less or equal to gx for all x in the interval 0 to infinity. So this function is dominated by some integrable function. So therefore we can apply the theorem that's in the lecture 2 in lecture 1, I think. In lecture 1 that the first theorem of the lecture 1 which states that if we have a function e power minus xt, if we have a function f from x plus g to r, such that function is Lebesgue integrable, that function is Lebesgue integrable, that function is Lebesgue integrable for each t fixed, and e power minus xt sin x over x is less or equal to some Lebesgue integrable function, then by that theorem we can see this limit t approach to infinity, integral f of t actually, which is equal to limit t approach to infinity. What's f of t? This is 0 to infinity e power minus xt sin x by x dx, and but this limit is equal to integral 0 to infinity limit t approach to infinity e power minus xt sin x by x dx, but this limit is equal to 0 because this t is approaching to infinity, x is a positive number. So this means that this limit is equal to 0, which means that the integral is equal to 0. So thus we have seen that limit t approach to infinity, f of t is equal to 0. Next we verify that. F dash t is equal to minus 1 by 1 plus t square for all t positive. So this is again simple. We can apply the second theorem of lecture 1 here. that the differentiation of the integral is equal to the integral of the partial derivative, that we can apply. This f dash t is actually the differentiation of the integral with respect to t. It will be equal to the integral the partial derivative, integral of the partial derivative. So that integral of the partial derivative is equal to minus 1 by 1 plus t square actually. So how do we do that? In order to establish this star, let's name it double star, okay, and name this one as star. So in order to establish double star, we have to check whether the partial derivative is bounded by some Lebesgue integrable function or not. If it's true, if it is bounded by some Lebesgue integrable function, that partial derivative of the integrand, then we can do this. So then we can say this f dash t is equal to the integral 0 to infinity partial derivative of the integrand. So for that, the partial derivative of the integrand function should be less or equal, should be dominated by some Lebesgue integral function. So we note that the partial derivative. We note that this partial derivative of the function e power minus xt sin x by x, that's the integrand function. The partial derivative, if we integrate this, sin x by x is a constant with respect to t, so we have to integrate e power minus xt only. Its integral is equal to e power minus xt into minus x, and x will go. This will be equal to minus times. This will be equal to minus times the e power minus xt into sin x. This, okay. So we can see that this for each positive number, for each a positive, we have this for each a positive okay, so this is e power minus xt into sin of x into sin of x. So this is true for each x greater or equal to 0, okay? And for each fixed a positive, and for each fixed a positive, we have the following inequality. We have the following inequality, that's we have this e power minus xt into sin x by x is less or equal to e power minus ax, where this t is greater or equal to this t is greater or equal to a, okay? If t is greater or equal to a, minus t is less or equal to minus a, so, and sin x by x is less or equal to 1, and we have also this inequality e power minus xt into sin x, this is also less or equal to e power minus ax for each t greater or equal to a. So that means this function, this partial derivative is dominated by this function e power minus ax, which is Lebesgue integral. For each a positive, this is the Lebesgue integral, because for a positive we have seen that the integral, the improper integral of this function always exists, therefore this function is Lebesgue integral. Okay, so we can apply the second theorem of that we have done in the first lecture of this section, the second theorem. Then therefore what is f dash t? Therefore f dash t is equal to d by dt of f of t. F of t is 0 to infinity e power minus xt sin x by x dx, and this is equal to the integral 0 to infinity the partial derivative of this function. This is equal to 0 to infinity del by del t of e power minus xt sin x by x dx, and that's equal to integral 0 to infinity e power minus xt into sin x dx. Then you do integration by parts. We know the integral of this. It is like e power ax into sin of dx. That we know how to evaluate this integral. Where to use the integration of by parts. So we have this. Then we apply the limit. Okay. We have let's name it triple star. We have this integral 0 to r, where r is any positive number, e power minus xt into sin of x. This integral is equal to, you do integration by parts, and you will see this is finally this is equal to minus times e power. This is very simple. You can do this integral e power minus rt into t sin t into t sin t plus cos of t divided by 1 plus t square plus 1 by 1 plus t square plus 1 by 1 plus t. So now letting t approach to infinity, r approach to infinity, we get this 0 to infinity e power minus xt sin x dx. This is equal to, if t is approaching to infinity, this will be equal to this is equal to minus 1 by 1 plus t square by letting r approaching to infinity. This will go. So this is minus 1 by 1 plus t square. So here is some mistake. This integral 0 to r e power minus xt sin x dx. This is equal to minus times e power minus rt. So this should be like minus terms. Okay. So then this will be equal to minus 1 by 1. You verify this. This integral. That's very simple. Or at the end I will see this integral. I will check this integral. Okay. At the end of this lecture. So this 0 to infinity e power minus xt sin x dx is equal to minus 1 by 1 plus t square for all t positive. This is true for all t positive, not for t equal to 0. Okay. Now what's double star? What's double star? Now we integrate double star. Let's keep it here as it is. We have this f dash t that we have already seen. It's equal to minus 1 by 1 plus t square. This is f dash t. Let's integrate this between the limits t and t naught. Integrate this function t to t naught. Integrate it from t to t naught. Then we will see this is equal to f of t naught minus f of t. Okay, and integral of this is equal to, we can see the integral of this. What is this tan inverse of t? Then we apply the limit minus tan inverse of t. Then apply the limit. This is t to t naught, and that's equal to minus f of minus tan inverse of t naught plus tan inverse of t, or that's equal to minus arc tan t naught, or you can say this is equal to arc tan t minus arc tan t naught. Okay. Now letting t approach to infinity, we get this is equal to 0. So f of t naught is equal to, letting t approaching to infinity, this is tan inverse of infinity, that's equal to pi by 2. So it's pi by 2 minus, because this is equal to pi by 2, tan inverse of infinity is equal to pi by 2. So arc tan t is pi by 2. Okay, this is as it is, arc tan t naught. So thus we have seen that f of t naught is equal to this. So which means that what's f of t naught actually? It's actually the integral. This means the integral 0 to infinity e power minus xt naught sin x by x dx is equal to pi by 2 minus arc tan t naught. Okay. Now we have case second. If t naught is equal to 0, then we evaluate. Then we evaluate integral 0 to infinity sin x by x dx. As already seen that in our first lecture, that since we know that integral 0 to infinity mod of sin x by x dx does not exist. So therefore the Lebesgue integral of this therefore sin x by x is not Lebesgue integrable. So therefore sin x by x is not Lebesgue integrable. But we will see that the improper Riemann integral, in fact the improper integral 0 to infinity sin x by x dx exists. We will see that this integral exists. So for this, let's choose any s and t for any numbers. Let 0 less than s less than t be any two numbers. Then what's the integral? Then we try to evaluate this integral. The integral s to t sin x by x. Do integration by parts. Keep 1 over x for integration and sin x for differentiation. Not sin x for integration, 1 over x for integration. So what's the integral? So 1 over x as it is because it's for differentiation. Okay, and the integration of sin is minus cos x. So limits s to t minus integral of differentiating function. Differentiate 1 over x. The differentiation of 1 over x is minus 1 over x square into minus cos x dx. So it's equal to, let's apply the limit. It will be equal to minus cos t by t and plus sin t by sin s by s. So it's sin of s divided by s minus sorry, not sin, it's cos actually. It's cos s by s minus cos of t divided by t minus it's just minus integral cos of x by x square dx. Okay, now let's try to find its mod. This implies mod integral s to t sin x by x dx. It's equal to the mod, it's cos of s by s minus cos of t by t, then minus integral s to t cos x by x square, because since we are doing the just Riemann integration, so here cos of s is less or equal to 1, it's 1 over s plus 1 over t using triangular inequality plus integral of this. That will be the integral mod of the integral of the mod, but cos x is less or equal to, it's just 1 over x square, which is a non-negative number. So this is equal to 1 over s plus 1 over t plus, now integral of 1 over s x square, it will be x power minus 2, then you can over plus 1 to the power, it's minus 1 over x, just 1 minus 1 over x s to t, and that's equal to 1 over s plus 1 over t, then plus what's this? It's the upper limit is minus 1 over t plus 1 over s, so it is 1 over s minus 1 over t. Okay, so this is just 2 by s, it's equal to 2 by s. So we have seen that thus mod of integral s to t sin x by x dx is less or equal to 2 by s. So which is less than epsilon whenever s by 2 is greater than 1 by epsilon. Take this as m. So for each epsilon positive I can find m which depends on epsilon such that this integral is less than epsilon for each s greater or equal to twice m. Okay, whenever s is greater or equal to 2 by epsilon, you can write here and this is your m, 2 by epsilon. Okay, so also it's true for every t. So we can say therefore mod of the integral s to t sin x by x dx is less than epsilon whenever s comma t is greater or equal to m or greater than m, you can say. So thus this function is that we have already seen that theorem. Thus integral 0 to infinity sin x by x dx exists. So now we try to evaluate this integral. What's the value of this integral? That's very important. To find the value of the integral is very important now. We note that the limit n approach to infinity integral n to n plus 1 sin x by x is equal to 0. So we have this integral n to n plus 1 sin x by x. If you want to find the mod, this is less or equal to, I think what's s to t, it's 2 by n, less or equal to n, so that approach to 0 as n approach to infinity. So this means limit n approach to infinity integral n to n plus 1 sin x by x dx is equal to 0. So this should be noted. This limit is equal to 0. Now for each n we define f and t. For each n greater or equal to 1, let's define the sequence. Okay, f and t is equal to 0 to n e power minus xt and sin x by x. For t greater or equal to 0, let's define this sequence. Obviously this is this integral exists because at 0 this also exists, so therefore this integral actually exists. It's in fact its mod will also exist for 0 to n, not for 0 to infinity. Then what's fn of n? What's this? It's equal to 0 to n e power minus nt and sin n by n. In fact, we try to find its mod. So this is less or equal to mod of this, but sin n by n is less or equal to 1, so it's less or equal to integral 0 to n e power minus nt dt. E power minus nt, it's nx here. Okay, t, you are choosing t equal to n. You are choosing t equal to n, not x equal to n. Okay, for t equal to n, it's minus xn minus nx. Okay, see, minus nx. Okay, this thing, and this value, it's just e power minus nx by n. You are integrating it 0 to n, and that value is, we first give the lower limit because it's minus term in this actually. By taking its lower limit, it's 1 by n, or you can say it's 1 minus e power n square divided by n, but that's always less or equal to 1 by n. That's always less or equal to 1 by n, because this thing is a positive number, e power minus n square, it's less or equal to 1 by n. So fn, mod of fn of n is less or equal to 1 by n. So that means mod of fn of n is less or equal to 1 by n, which means that limit n approach to infinity, fn of n is equal to 0. Now we apply the second theorem of lecture 1. We have fn dash t, that's d by dt of fn t. What's fn t? Fn t is the integral, it's the integral 0 to n e power minus xt, where x is t is positive, dx, and this is equal to the integral of the partial derivative. This is equal to the integral of the partial derivative. This is equal to the integral of del by del t of e power minus xt sin x by x dx. We are applying that theorem, and that's very simple. Why we are applying this theorem? So I have not discussed now that because you have to check that partial derivative is dominated by some Lebesgue integral function. That's very simple. This is the integral of this. So you are differentiating partially with respect to e power minus xt into minus x. That x and x will go. It's just e power minus xt now sin x dx. This one. And that the value of this integral, it's a value integral. It's the value integral, and its value is equal to e power minus nt times t sin of n plus cos of n minus 1, okay, divided by 1 plus 2, integrating by parts. You are integrating this function by parts. Okay, you will see this integral is equal to this is 0 to n. This is integral 0 to n. Now letting here n approaching to infinity, we will see this will be equal to 0. So this is 0. It's minus 1 by 1 plus t square. Yes. So this implies that this is actually, what's this? This is a fn dash t derivative of this. Okay. Now let's taking this n approaching to infinity. This implies limit n approach to infinity, fn dash t is equal to the limit of the RHS, that's equal to minus 1 by 1 plus t square. And you can see that page here, because e power minus nt approach to 0 as n is approaching to infinity. So this is 0 into that factor, and then minus 1 divided by 1 plus t square. So this is true for all t positive. We are choosing t positive here. Also, we can see this mod of fn dash t. What's this modulus? And you will see this is mod of fn dash t. Okay, mod of fn dash t. This is equal to mod of, what is fn dash t? That we have seen, that's equal to e power minus nt t sin of n plus cos n minus 1 divided by 1 plus t square. And let's apply the triangle inequality. It's less or equal to 1 plus this, okay, but sin of n is less or equal to 1, cos of n is again less or equal to 1, so it's less or equal to 1 plus e power minus nt times t plus 1, okay, divided by 1 plus t square, divided by 1 plus t square. So mod of fn dash t is less or equal to this function. Mod of fn dash t is less or equal to this function. This is true for all t positive. Okay, for all t positive this holds. and this function is Lebesgue integral for because it's actually independent of x. So it's for any neighborhood of v of t, this function is Lebesgue integrable. For any so we have seen this mod of f and dash t is less or equal to what? It's less or equal to 1 plus e power minus nt, 1 plus e power minus nt times 1 plus this 1 plus t times e power minus nt, 1 plus t times e power minus nt divided by 1 plus t square. So this is it. This is true for all t positive, f and dash t. And this dominating function for specific case, this is Lebesgue integrable. It's not and it is just t here, okay? E power minus t. It's e power minus t only. So let's see the previous page. It's e power minus t only. Where? It's e power minus t, not nt, okay? It's e power minus t. It's e power minus t, okay? This one. So here it should also be e power minus nt, f and dash t. Yes, f and dash t, there is e power minus nt. Yes. So actually this minus n is actually greater or equal to 1, so minus n is less or equal to minus 1. So why it's therefore it's less or equal to this. You are choosing n is here 1 actually. So it will be less or equal to e power minus t. E power minus nt is less or equal to e power minus t, okay? So actually here it's e power minus t, but you are using this inequality, it will be it's less or equal to e power minus t. Okay, so this is less or equal to this function, but this function is Lebesgue integrable over 0 to infinity. Over 0 to infinity, this function is Lebesgue integrable in neighborhood. Not necessarily Lebesgue integral. It should be bounded by some constant. What's that theorem? That theorem states that okay. So how this function is Lebesgue integral? This is very important here. F and dash t is less or equal to this, but this function should be integrable over 0 to infinity, over the range 0 to infinity. This function should be Lebesgue integrable. It's a it's a constant thing, so its improper integral must exist there. Its improper integral must exist there, and the dominating function for this sequence, okay, for this sequence is Lebesgue integral over 0 to infinity. So if this Lebesgue integral with this function over 0 to infinity, we don't have any x here. So how do we do this? This function is Lebesgue integrable. Okay, this function should be Lebesgue integrable. Then we can apply the theorem. Then and only then we can apply the dominated convergence theorem. This is Lebesgue integrable. This is Lebesgue integrable. This function is Lebesgue integrable. Okay. it's a non-negative function. If this function is the Lebesgue integral over 0 to infinity, then improper integral must exist. But what is the improper integral of this function 0 to infinity dx? That's infinity into this thing, which is infinity, and because this thing is a positive thing, so how can we say this Lebesgue integral of this function exists? Unless we don't have certain function of x here. It should be, because constant function is not improper. Improper integral of constant function does not exist over 0 to infinity. It's just like constant function because we don't have fn dash t. Okay, so you are treating this as a function of t, not function of x. So this is not actually constant. This function is Lebesgue integrable. This function is Lebesgue integrable. Okay, because the improper integral, since the improper integral is 0 to infinity. Okay, now I got it actually. 1 plus t times e power minus t divided by 1 plus t square dt exists. So therefore 1 plus t e power minus t divided by 1 plus t square is Lebesgue integrable over 0 to infinity. Here x actually, it's expressed to x, not because we are dealing with the sequence of functions of t actually, not of x, f and dash. Okay, so this sequence is dominated by Lebesgue integrable functions. So you can easily verify this integral exists. This is not too hard. It's very simple to check. 1 over 1 plus t square, that also exists because it's tan of t, whose integral is tan of it's just pi by 2, and you have to check only this integral 1 plus t power minus t divided by 1 plus t square. That's again simple, that you can do yourself, this existence of the improper integral of this function. It's very simple. Now we define a new sequence. Let's define this sequence, and on that sequence we apply the Lebesgue dominated convergence. So define gn of t. Obviously we must have to define this like it's fn dash of t into characteristic function 0 to n. Everything is because what's gnt? It's equal to fn t on this range 0 to n, but on 0 to n it exists. Fn dash exists as it's Riemann integrable, therefore it's Lebesgue integral, and on the rest of the set 0 to n, on n onwards its value is 0. So we can say this gn, therefore gn is a sequence of Lebesgue integrable function, and not only this, mod of g and t is less or equal to mod of fn dash t. We don't need to mod for fn dash because in fact we don't need even the mod on this gnt because it's a non-negative function. So fn dash t, this mod is less or equal to fn dash, or you can put mod here. It will not create any confusion here. And but this fn dash t, it's dominated by Lebesgue integral function. So this sequence is dominated by Lebesgue integral function. Thus the sequence gn of Lebesgue integrable functions is dominated by Lebesgue integrable function. And one more thing, and what's the limit? And limit and approach to infinity gnt this is equal to limit and approach to infinity. It's same. It's just equal to, you can verify this. This is equal to minus 1 by 1 plus t square minus 1 divided by 1 plus t square. So therefore integral of g and t, limit of the integral of g and t is equal to integral of limit of g and t, which is equal to this. Now let's try to do this. Now by Lebesgue dominated convergence theorem, by Lebesgue dominated convergence theorem, we have limit and approach to infinity, integral 0 to n fn dash t dt. It's equal to, but on 0 to n its value is g and t, and for rest its value is 0. So it's equal to limit and approach to infinity. This is just 0 to infinity now, g and t dt. But this one it's equal to 0 to infinity limit of g and t, and that's equal to 0 to infinity. What's g and t? This is equal to minus 1 by 1 over t square. It's equal to minus 1 divided by 1 plus t square, and that's equal to minus pi by 2. That's equal to minus pi by 2. Okay. So again we have we have this integral 0 to n fn dash t. This is equal to fn of n minus fn of 0, and limit of this is equal to 0. So we can see this limit and approach to infinity, integral 0 to n fn dash t is equal to limit of this, that's equal to 0 minus fn of 0. It's limit actually, limit and approach to infinity. But on this side it's equal to pi by 2. On this side it's equal to pi by 2 actually. This side, this is minus pi by 2. Okay, actually this is minus pi by 2. This is minus pi by 2, and minus limit of fn 0. What's limit of fn 0? What's this? So this is equal to, this just equal to minus limit of fn 0. So thus limit of fn 0 is equal to pi by 2 actually, because this is equal to minus pi by 2 and that thing is equal to 0, because limit of fn n is equal to 0, that we have already seen, and that means limit of fn 0 is equal to actually pi by 2. So which implies limit n approach to infinity, fn 0 is equal to pi by 2. So finally we have this integral 0 to n plus 1 sin x by x. Actually we have to find the limit of this actually. This is equal to 0 to n sin x by x plus n to n plus 1 sin x by x dx. This thing we have seen, this is equal to 0. So let's apply the limit now. Now this thing, this is equal to 0 to n plus 1 sin x by x is equal to, what's this? This we have seen it, this is by definition it's equal to fn 0. Fn 0, its value is fn 0. Because fn t is equal to e power minus xt actually, 0 to n. So its value is fn 0 plus this integral limit n to n plus 1 sin x by x. So let's apply the limit now. Let's apply the limit and approach to infinity, and we will see that this limit is equal to pi by 2, and this limit is already seen, it's equal to 0. So this implies limit and approach to infinity 0 to n plus 1 of sine x by x dx is equal to limit and approach to infinity fn 0 plus limit and approach, because every limit actually exists, is n to n plus 1 sine x by x, so that this is equal to 0 to infinity sine x by x dx, and this thing is equal to pi by 2, and this is equal to 0. So this limit is equal to 0. So thus we have evaluated the integral, and this is 0 to infinity. So we have proved this actually. This fn of 0, just let me again, fn of 0, limit of fn of 0 is pi by 2. So limit of fn of 0 is pi by 2. But what's actually fn of 0? Is it what's fn of 0 actually? Gn. This is your fn dash. Okay. Fn t is less or equal to this. So this is your fn dash. What's actually fn? Yes, this is your fn of t is actually this. So what's fn of 0? That's equal to 0 to n e power minus x into 0, that's 0. So fn of 0 is equal to 0 to n sin x by x. So limit of fn of n is equal to pi by 2. So that is why the integral is actually, the value of the integral is pi by 2. Okay. So thus how we have proved this theorem, and this completes the section, this section of the unit. In the next section we have to see that we'll check that we'll try to find out the completion of CAB, because you know that the set of continuous functions is not complete. Actually, we know that CAB is not complete metric space where metric is defined by, with respect to submetric it's complete where metric is defined by, but with respect to L1 metric, if we define the metric by this integral 0 to a to b mod of f of x minus g of x dx, it's not complete. And we know that every metric space has a completion, and we know that every metric space has a completion, therefore CAB has a completion. Therefore CAB has a completion, and we will see that, set of Lebesgue integral function of power 1, not pth integral but 1th integral, okay? L1 is the completion of this CAB. So this will be the last theorem of this chapter.